don't stand behind any podium. Good morning, it's a pleasure to be here. I think I was a keynote speaker maybe 10 years ago at this conference. I always enjoy coming to this conference and being able to interact with some of the colleagues in industrial and systems engineering. The title of my talk today is Engineering Challenges in Human Spaceflight, and you'll see I concentrate a lot on our failures in the past, and that's for a reason. What we do is we fly in a very harsh and unforgiving environment, and if we make a mistake, many, many times it costs us loss of the vehicle and sometimes the loss of life. And it's important that we remember those lessons learned. It's important that we remember those incidents in similar programs. And I think that's very analogous to any industry that you might be in. And so hopefully you'll garner a little bit of what you can take away to your own organization through the course of this talk. As I said, spaceflight is a very inherently risky endeavor. The vehicles are extremely complex. You're flying in a very hostile environment, very dynamic conditions during ascent, extreme energies used to get the vehicles just into orbit. As you know, within the US space program, we've had 3 fatal accidents going back to Apollo 1. So we've kind of seen from the entire spectrum. Apollo 1 was sitting on the launch pad during a terminal countdown demonstration test when they experienced a fire in the capsule. They weren't even supposed to launch that day. It was a practice countdown. And then, of course, we had Space Shuttle Challenger, January 28th, 1986. That year, I was down at Fort Rucker, Alabama. I was an instructor pilot, and I had already been called to be notified that I was going to be interviewed for the astronaut selection process that year. And I was coming back into flight operations to turn in my aircraft key. I had flown some students that morning, and everybody knew I was going to go down and interview for the astronaut program, and they said, "Did you hear the news?" And I said, "No," and turned around and saw on television what was unfolding. Needless to say, they canceled the astronaut selection that year, but they did have a selection the next year. I interviewed, I was not selected, first failure. Very, very common. NASA doesn't want people to kind of wake up one day and say, "Yeah, that astronaut thing, I think I'll try that for a while." It's a career, it's a high-risk career, and it's something you really dedicate your life to. Many, many people spend decades at NASA. Some spend decades waiting to fly. I was fortunate to come in during an era where flights were occurring 7-8 flights a year, 5 to 7 crew members on a flight, and so hence I was able to get 4 space flights in my 15-year active career in the astronaut office. And then, of course, on February 1st, 2003, we had the Space Shuttle Columbia, which occurred during entry, but really that accident scenario started unfolding literally seconds into the flight. And I'm going to talk a lot about that accident today for many reasons. There's a lot to be learned. Of course, in the Russian program, we have also had some fatalities. They occurred very early on. You can see Soyuz 1, both the main and reserve parachutes failed. 1 crew member was killed during entry. And the next one that occurred was a rapid depressurization where 3 crew members were lost. So it was interesting because if you look at our history was we've lost vehicles on the launch pad. You know, obviously a lot of energy sitting at the launch pad, very, very high risk environment. We've lost Challenger during ascent. And so we kind of lapsed into this thinking in the American program that most of the risk was in launching these vehicles. And we did things on my first flight, like 2 minutes into the flight, once the solid rocket boosters had separated, its visors off, visors up, oxygen off. And most people, I even heard a comment during launch, 98% of the risk is gone. And I think that's because we really didn't have an appreciation for all the risks during entry. And of course, Space Shuttle Columbia showed us. And during entry, you come in, at least in the Space Shuttle, even at the altitudes And atmospheric conditions, the heating on the vehicle gets up to about 2,400 degrees Fahrenheit on the leading edges of the wing and the nose. So obviously a very harsh environment. So why do we learn from our past and especially concentrate on our failures and close calls? You know, sometimes I feel a little bit guilty that I'm not out there talking about all our successes, but our successes are fairly well publicized. And in fact, I used to say, especially after Columbia, we had fallen into this, we were a victim of our own success. We made it look so easy that we launched 6, 7 spacecraft a year. We did all these fantastic missions, servicing the Hubble Space Telescope, building the International Space Station. Time after time, we sent people outside on an extravehicular activity, spacewalks, which is also a very dynamic environment. And we made it look easy. We made it look easy because we put thousands of hours of training into it, everywhere from the ground personnel that are helping us on the mission and the crew members that go fly on them. But it's really, really important that we concentrate on our past failures as well as our successes. Almost more so to concentrate on our past failures. So what we've done, and what I'm about to show, and unfortunately it doesn't show up very well on the screen, and the reason why it doesn't is because there's a lot of information on it. And what our safety organization did was they mapped all of the human spaceflight incidents, accidents, and close calls, and they mapped it whether they occurred in ascent, on orbit, or entry. They included some of the Russian missions. And why do we do a graphic like this, which is a little bit overwhelming the first time you see it? I think the first thing you're going to say is, wow, there's a lot of close calls on there, and there's a lot of incidents and accidents on there. And why do we do that? Is to fully understand the failures. You know, do we understand why that failure occurred? Do we understand what prevented its detection? What controls could have helped exacerbate the failure or even prevent the failure? And then it's equally important to look at our close calls. You know, those instances where we literally dodged a bullet. Because we need to understand, well, what mechanisms were in place to help us detect those, to help us control those failures. So here's a graphic. And I heard a wow, and that's what I usually hear when I show this. So on the left side of the screen, you see the ascent, and anything in yellow with a red box around it is a fatality. In the middle, you see Earth orbit at the bottom, lunar orbit at the top, and to the right, you see entry. So the first thing that tells you is, if somebody thinks most of the risk of flying human spaceflight is in the ascent phase, you're wrong. Because our history tells us that risk is spread out through all phases of flight. You know, I even used to say there's relatively few things that can kill you on orbit. But some of the things that can are extravehicular activities. And if you follow the news, it was about 2 years ago, where we had an astronaut almost drown in his suit because we had a water leak. Of course, water started pulling into the helmet, and the helmet started filling up with water. And you know, because of the surface tension of the molecules of water, it started to form a ball, and one kind of went right over his nose and mouth. So he was very, very lucky. We stood down doing spacewalks for a fairly lengthy period of time to understand that. We've also cut gloves outside. We really worry about micrometeorite orbital debris damage on spacecraft. When they do hit, especially on metallic structures, it tends to be almost like a bullet and causes a lot of sharp edges. And we were experiencing cuts in the glove. Luckily, we have never cut into the pressure bladder. But again, close call, we've dodged a bullet. We've had electrical shorts. We had an electrical short during ascent one time. That ascent, that AC bus took out 2 main engine controllers on 2 different engines. Thank goodness for redundancy. We're very big on redundancy in human spaceflight in particular. But we were literally 1 failure away from losing an engine, which is a real catastrophic failure. A little bit about that one. One of the things we do as a control, we say separation of critical functions. So an electrical bus, you know, we literally have separate wires. Good idea. separate feeds going to those engine controllers. We have redundancy. Unfortunately, in the vehicle, they bundled all of those wires together, and during ground processing, inadvertent damage occurred, probably due to somebody stepping on that wire bundle. The frayed wires touched, of course, during the most dynamic phase of flight, which is ascent, and the vibrations ultimately caused a short. I do have a few of those handouts if anybody's interested, and I can certainly get more of those. The Aerospace Corporation developed something that's a very interesting read, and they developed something called 100 Questions for Technical Reviews. And these are just some of them that are embedded in their 100 questions. And for each one of their questions, they trace it to 1 or 2 or 3 fairly substantial incidents. And they're mapped in the document, and I have the reference at the bottom. But you can see some of the things that as you go into, and the nature of the work that we do now in the NASA Engineering and Safety Center, many times we'll be called in to do peer reviews of different NASA programs and projects. And so very frequently I will call up this document and run through this list of questions to make sure that the review is exceptionally thorough. That third bullet contains a phrase that we actually outlawed during the return to flight of the Shuttle time frame, which is out of family. So out of family at NASA became sort of, well, it doesn't work the way we really intended, but it works okay, and nothing's ever happened. And it causes you to lapse into this false sense of security. So what does that mean? We didn't hit the red line, but the engine was operating much hotter than we ever anticipated, and much hotter than intended nominal conditions. Didn't redline, so we would call that out of family. And we would treat that completely differently. We wouldn't treat it as a failure. And we learned after Columbia that out of family condition eventually caused the destruction of a vehicle and the loss of 7 lives. My late husband used to say that launch day for the crew and the family was the most spectacular day of your life and the most memorable day of your life. Family members like it, they're treated kind of like royalty, and they're ushered around with police escorts, and a lot of them like that. And my husband used to say the only reason they're doing that is in case this becomes the most memorable day in our lives for all the wrong reasons. Most of the time, most of the families got to enjoy it as one of the most pleasant memories they ever had in their life. This is our crew. I am somewhat vertically challenged, but I flew with several giants. The guy in the front, the commander, the Navy pilot, is 6'4", 225. So in our crew photo, we're standing side by side. We call it the anthropometrics of NASA demonstration. But what's really neat is you stay in the same building that Neil Armstrong stayed in before his launch. You walk down that ramp, and that's what's going through your mind of all the people that have passed in front of you, some who have made it through their incredible experience, and some who have not. So when it goes well, it's pretty spectacular. 3 main engines, 375,000 pounds of horsepower. T-minus 6 seconds, say light, T-minus 0 solid rocket boosters light. Boom, you got 7 million pounds of thrust propelling you off a launch pad. And right here, we're already going 100 miles an hour, ready to talk to the launch tower. That's my little head bobbing up and down. Keep sight on the displays. And of course, we roll head down to reduce stresses on the vehicle. No, we're not looking out the window right now. We are staring at the main engine displays and the electrical displays. First stage ascent and shuttle was fairly dynamic. As you see, they come in, they strap you down very, very tightly. 3 or 4 people are yanking on your straps. And once you start into ascent, it's actually a little painful to be laying there waiting. But once you start into ascent, you're kind of thankful they did. course, we only rode the solid rocket boosters for the first 2.5 minutes. Like I said, I think in large part because of the Challenger accident, most people felt that when the solids departed, a lot of the risk was gone. And of course, it was not. So, 1 year later, now if you notice, our mission in March of 2002 was STS-109. This is STS-107. Well, how did we get out of order? Well, we got out of order. We were both on the Space Shuttle Columbia because we were on the Hubble servicing mission. Hubble started to experience some degradation of their systems, affecting their pointing system. Of course, affect the pointing system of the telescope. That's not good. So we were accelerated in front of the 107 crew that was a biomedical research mission. So our vehicle that took us to orbit and back, was poised again 1 year later with the STS-107 crew. Unfortunately, here's what happened during their launch. So in the video frame, and I'll play it again because it goes by pretty quickly, in the still photo, you can see the arrow pointing to the debris that came off the external tank. And it's foam debris. Foam is on there because we've got cryogenically stored hydrogen and oxygen in the tank. And so to prevent icing, we've got foam insulation on the tank. Remember I talked about that out-of-family condition? Well, the out-of-family condition was foam came off that tank every single flight. We used to paint the tank. That's a lot of additional weight, a lot of additional mass to orbit. Wasn't necessary, and so we stopped painting the tank and just flying with foam insulation. And we started to liberate a lot of foam. It took us until after the Columbia accident to really understand the physics behind why we were losing foam off the tank. And had to do with a phenomenon called cryopumping that was causing delta pressure and literally popping the foam off the tank as the levels decreased. We didn't even study it enough to understand the phenomenon because foam always comes off. It's normal. Foam always comes off. But if you see in the video image that I'll play again, you can see it come down, strike the wing. We know it struck the wing because you can see the spray. As soon as it hits, you see the spray. So we had video evidence during the flight, shortly after ascent, foam hit the vehicle. Engineers were worried about it. Engineers tried to talk to people about it. Engineers tried to get additional imagery from other governmental assets and were unsuccessful. Almost every single shuttle flew a robotic arm, except this one. Because they were a biomedical mission, they had no robotic arm operations plan. So for mass savings and to enable them to take more payloads, scientific payloads and experiments, they took the arm off this flight. There was no way for them to know what size hole that foam had created in the wing. So from that point on in ascent, and I'll show you from some of the ground testing, they had a 13-inch hole in the wing, in the port wing. Didn't cause any problem on orbit, didn't even notice it. So this mission went on for almost 2 weeks. As I said, engineers, particularly at the Johnson Space Center, where we have the design engineers, very, very concerned about this strike. The next indication was on entry. So on entry day, they start to come in. They start to get into the region of peak heating. And they start experiencing anomalies. The very first thing they got was a left main tire pressure message. They then got a fairly rapid series of additional messages, and in the control center, you hear different people reporting in, and if you've never seen the control center at NASA, you've got an environmental control officer, you have a mechanical systems officer, you have a guidance and navigation officer. Everybody starts reporting in different things. A flight to the flight director, a flight, I got a left main tire pressure message. A flight, I've got this sensor message. He continually quizzes the control team, is there any commonality? Is there any computer card in which all these sensors are going to? Is there any wiring commonality? The entire control center is stumped, and then they lose comm. Loss of comm, not all that unusual, except the loss of comm continues. Now, I'm watching at home because I wasn't working this mission. I'm watching at home, kind of listening to all this unfold, and I'm thinking, this doesn't sound right. Was my first indication. Just kind of had that feeling in my gut. Loss of comm continues. The CAPCOM goes all the way back to the initial capsule communicators. Always an astronaut that talks to astronauts on orbit. Continually says, "comm check." No response. "Comm check." No response. The control center is now looking at static data. They're stumped. They can't figure it out. They're still trying to figure out what's going on. The instrumentation and communications officer is not thinking anything really bad is going on, thinking they were having communication problems, so he's hard at work. And finally, that image that I showed that was taken from Dallas, Texas, was shown on the Houston TV stations. And one of the flight directors who was off duty called in on a telephone and told the control center, "You've lost the vehicle." Believe it or not, that control center was blind. There's no sensor that goes off saying you've lost the vehicle. That's how we knew. We saw the breakup. That debris field reached from Dallas all the way into the border of Louisiana. And in fact, if they had waved off one more orbit, which they talked about because of weather conditions, the accident would have taken place over Houston, Texas. The debris field actually started in California. They found evidence of some of the first tiles that were found over California. So, after the accident, of course, Accident Investigation Board was commissioned, as it was after Challenger. And I think the most disturbing thing is that that accident board came back and said there's really 3 causes. And 2 of them should be really disturbing to you as an organization. There's clearly a physical cause. That foam coming off the tank, the orbiter flying in a debris field in which it was never intended to fly in, is a huge issue. The second one was the safety culture at NASA. You know, NASA's known for its can-do spirit. The downside of that is that can-do spirit can cause you maybe to take more risks than you really should. And so you can see the quote there, the accident was probably not an anomalous random event, but likely rather rooted to some degree in NASA's history and human spaceflight programs and culture. And finally, organizational issues. Space Shuttle program does not consistently demonstrate the characteristics of organizations that effectively manage high risk. And so we spent the next years, and we're still spending those years studying, well, how do you manage, how do you do engineering in a high-risk environment? Ironically, we got this criticism, and then within a year after the flight, not the same investigators, but the media and others were calling us risk averse because we stood down. We stood down for 2.5 years. We wanted to make sure it was safe to put people on. And then suddenly we're risk averse, so we had to manage that environment. So the physical cause of the accident, 1.67 pounds of foam took down a 200,000 pound orbiter. So it departed at 81.7 seconds, and as I said, caused a hole in the wing, and then the superheated air penetrated that wing, eventually burned through the wiring, so all the sensors that were failing was because the wiring was burning through and eventually caused the failure of the wing. That system, that vehicle was so robust, if we'd gone about another 4 seconds, we would have been out of the area of peak heating and might have survived. So after the accident, they studied, they had this theory it was a foam, and of course a lot of people said, no way, a piece of foam can't take out the orbiter. So we went over to Southwest Research, and we shot foam at the reinforced carbon-carbon panels at the projected velocity, and you can see what the effect was. Even more disturbing is this video. That's a camera inside the wing. That's what happened in the accident scenario. about a 19-inch piece of foam, less than 2 pounds, and that's the damage and destruction it caused on the leading edge of the wing of the vehicle. So remember all those flights, going back to the earliest days of Shuttle, where we lost foam? We literally were dodging bullets, and we just didn't know it. So we lost a crew and 7 people. It was one of those phases in my career that was a turning point. You know, that's something you'll never forget. I was involved in the accident from the first couple of hours. I was deployed to the field for the crew recovery operations. Astronauts were involved in that, and that is a life-changing event. And then I came back and I was working in engineering, working in robotics. I thought that's what I wanted to do. And I got a call one day and said, we want you to lead the shuttle safety office. And it was the chief astronaut asked me to do this, and I said, did you just say shuttle and safety in the same sentence? Because I don't think I like what I'm hearing. And he said, yes, because every single manager was fired. Now remember, all government employees, I was actually active duty military at the time, government employees are typically moved out of a position. That's the equivalent of firing. They're moved to a position of lesser authority, lesser responsibility, and quite frankly, many of them left the agency after that. Many of them left the agency after that. So we had a whole new team in place, and safety in particular was highly criticized by the Accident Investigation Board. So one of the first things we had to do is to say, what are all the steps we need to take to safely return this vehicle to flight? Well, the very first thing you do is, so we sat down and the managers were kind of stumped, and everybody's making suggestions. Everyone in the world, literally, our phones were ringing quite a bit at NASA during those days, and it was all good feedback. But the first thing you would do is step back and say, well, let's use our system safety engineering expertise, and we'll walk through the hazard reduction precedence sequence. So the very first thing you want to do is eliminate that critical debris. You can't do it. It is not possible. All the various sources of debris, to include bird strikes, to include micrometeorite orbital debris on orbit, to include pieces of paint coming off the launch pad, to include bricks coming out of the flame trench, which I believe happened after Columbia. A bunch of bricks shot out of the flame trench right at launch. So we couldn't do that, and so then we had to have a series of safety and warning devices and special procedures. And I will tell you the two at the bottom were extremely controversial. So we had to develop a method to repair that reinforced carbon-carbon, also to repair our thermal protection system tiles. At one point, even the crew office was opposed to the tile repair. And then we finally flew it as a test objective, a test on orbit, gain their confidence. And the bottom one was extremely controversial the day we walked in and said, we will not fly the shuttle, we safety will not fly the shuttle unless we now have a crew rescue capability. All the way up to the chief of the agency, and I got to brief the chief of the agency on many occurrences. That was a tough sell. And at one meeting, we had a little meeting before we had a meeting with the administrator, and the program manager looked at us and said, this is one of those times we have to stand up, stand shoulder to shoulder and say, not this team. If you want to launch the vehicle without it, we're all going to step down and you're going to have to put somebody else in their jobs. And that's what we did. John O'Keefe, as the administrator, said, you guys are the experts. I trust you. I'll go tell Congress we're not flying for another 6 months. Cultural and organizational issues are a much harder thing to change, especially for an organization that's got that can-do spirit, that takes risks, that puts people on the moon for the first time, that puts people into space and makes it look like a routine business. But when you see something in an accident report like you see in the Senate, we're convinced that the management practices overseeing the shuttle program were as much a cause of the accident as the foam that struck the wing. You got to really step back and examine what you're doing. One of the first things we did, as I said, engineers were speaking up or trying to speak up. And one of the things that we try to do today is proactively solicit alternate positions. We even go to the point of, we don't call them dissenting opinions because that might have a negative connotation. We call them alternate positions. And we very, very much proactively solicit those. It's been a while though. There's not a lot of change in the environment in the International Space Station. You know, it's been flying since 1998, been flying very safely. Orbit is a somewhat quiescent environment until failure occurs and then it becomes not so quiescent. But it's certainly not like launching a vehicle. And so it had been a number of years since we really had some controversial alternate positions, but we have had some of those recently. The second thing you see we did is really strengthen systems engineering and integration and safety and mission assurance. Those are two areas that over time had degraded, because if you work in systems engineering or you work in system safety, how do you show the benefit of that? Can you really go tell a program, you're not having accidents because we have a very strong systems engineering and integration function? And we're looking across the spectrum of all the interfaces, and we're looking for those issues, and we're fixing those issues. Same thing with safety. You know, are those mandatory inspection points? Are those additional quality steps? Are those preventing accidents? Well, now we have documentations where we can trace back our close calls and say, yeah, we are buying you down risk. We are buying you down accidents. But over time, because of budgets and schedules, those things have attrited quite a bit. I think the most disturbing thing about the Columbia accident, and Sally Ride, Dr. Sally Ride, who's passed away, was on both of the boards for Columbia and Challenger. And at one point, listening to all the things that had occurred in the Columbia decision, she coined the phrase, "This is echoes of Challenger." Really, really bad. That means we didn't learn the first time, we didn't learn our lessons, because many of the things that had occurred in the decision process to not further research that foam strike and the potential damage that it caused were very similar to what occurred during the Challenger accidents. Diane Bond, and who we met, who came down and helped us after the accident, helped us with some of our organizational and cultural issues, coined the phrase normalization of deviance. And we still talk about that today. You'll still hear speeches to our employees about be wary of that normalization of deviance. Those out-of-family conditions that we say, yeah, it always works that way, it always runs hot, never exceeds a red line. You know, it's just seems to be that, you know, that sets systems capabilities or parameters. And so both the Challenger, the O-ring erosion and the solid rocket boosters, and the debris strike on Columbia, both of those failures were acknowledged. They were discussed in somewhat detail. But in the end, we made the wrong decision. And I think the wrong decision because we didn't appropriately characterize or fully understand that risk, especially the catastrophic nature of the risk. So why is that? One of the things, again, that we were chartered not to do is not look back and say, well, we flew 50 missions safely in this configuration. Just because you've flown 50 missions safely doesn't mean the 51st isn't going to cause an accident. It's hard to do. You want to use that as, we rely on flight rationale, we rely on a whole host of things, test data, analysis data. And a lot of our flight rationale was based on history. And we said, you know what, we can't do that anymore. We just demonstrated that we flew all those missions up to STS-107, and then on that mission, lost the vehicle. Again, they launched in February of 2003, and in October of 2002, they had foam shedding from this bipod region, this ramp region on the external tank, that was so large and it hit the skirt, the bottom skirt of the solid rocket booster. And they talked about it, but it was a way in which they characterized an anomaly. They called it an action item. Totally different than in-flight anomaly. You have to thoroughly understand it. You have to have flight rationale to fly the vehicle. Again, they said, nah, that's an action item. We'll just kind of look at that. as time permits. Again, some more echoes of Challenger. In both Columbia and in Challenger, organizational structure can interfere with information flow. And what do I mean by that? If you're a fairly young engineer and you're at GS11, are you going to go up to that SES program manager and tell him he can't fly the space shuttle? Tell the chief of the astronaut office he can't fly? So we had to create a system by which everyone, and we said anybody can throw the flag, anybody can stop a launch, but in practice it's a lot more difficult. And I try to always remain cognizant of that. I always try to look and read people's body language, look at their faces as we're having a very in-depth technical discussion, especially one that's very controversial, and look for those people who are still uneasy. And if I think they're uneasy and they're not speaking up, I'll go over to them and say, what's bothering you? One of the things I did as a safety manager is I told everybody in the shuttle program, if you've got an issue and you don't feel comfortable speaking up, come see me, tell me what the issue is, and I'll represent you, and I'll make it sound like it's coming directly from me. Nobody will ever know that's not how the way I personally feel. And so our managers are chartered with doing that. It's one thing if you work in a very high-risk organization, you work with engineers that tend to not be extroverts and tend to not want to slam their fist on the table, especially as a young engineer. It's just sort of by our nature, we're a little more introverted than, say, other professions. And so as senior engineers, we need to help facilitate that communications. The other thing, the last bullet down there, is we created independent technical authorities for 3 areas: engineering, safety, and then crew health and medical. And I'll talk a little bit more about that as independent technical authorities. So why did we stop flying the shuttle? Well, this was a statement in the Columbia Accident Investigation Report, and it's pretty scathing, right? If you wear a NASA badge like I do, based on our history of ignoring recommendations or making improvements that atrophy with time, the board has no confidence the space shuttle can safely be operated for more than a few years based solely on renewed post-accident vigilance. I was a military aviator for a long number of years. Your post-accident vigilance is a real thing. Right after you lose a crew, everybody's safety awareness is at a high, and it does tend to erode with time. And it's a challenge to not allow that to erode with time. And you do need constant reminders. So what did we do with that? We didn't just stop flying the shuttle because we had an International Space Station to build. The shuttle payload bay is 60 feet long, 15 feet across, and most all the major components on the space station were designed to fit in the shuttle payload bay and get carried to orbit that way. We had no other vehicle to do it. And we wanted to finish building this multi-billion-dollar orbiting laboratory. And so, but it was our mindset. All the flights after Columbia we considered test flights. Now, as a military aviator in a test flight, what does that mean? That means minimum essential crew. So what's that mean? We stopped flying, I'll use a nice word, I almost said the wrong word, I almost said strap hangers. We stopped flying those people who were not professional astronauts. Because there was a phase at which we did fly, I'll call them visitors, on the space shuttle. And occasionally the Russians still fly visitors on the Soyuz. Yes, they're trained, but they are not trained anywhere near to the level of a professional astronaut. The next thing is all missions were restricted, at least initially, to building and finishing the assembly of the International Space Station. When Mr. O'Keefe stepped down, Mr. O'Keefe was adamant we would not fly the Hubble servicing mission that was scheduled because we didn't have a crew rescue capability. The reason why we felt comfortable doing enough to get back to flying is because if something did occur, the crew could use the International Space Station as a safe haven. Now, early on, as we started after the Columbia accident, we didn't have a substantial amount of consumables on the International Space Station, and now you've kind of overloaded it with a shuttle crew of 5 or 6 people, in addition to the 2 or 3 astronauts who were already living there. And so that time that the International Space Station could sustain that larger crew was sometimes measured in days and weeks. Near the end of the shuttle program, it got to be months. And so we didn't have that capability for a Hubble servicing mission, but they developed a technique to bring up another shuttle and literally transfer, by using the arm in spacesuits, transfer the astronauts from one shuttle to another and do a crew rescue. And so an independent team was commissioned. I led that team to determine whether there were enough risk mitigations to substantiate the risk. I was selected because I'd flown on a Hubble mission. I knew what risk was involved, and we decided to fly that mission. So that was the only mission flown after Columbia that was not to the International Space Station. And then finally, the shuttle fleet was retired in 2011. So that's why the shuttle fleet was retired. So I put these in here because frequently, and it somewhat amazes me, I've even been in academic conferences where people say, well, what are you guys doing now? You know, now the shuttle's retired, what are you doing now? Are you flying? You know, I've even heard people think NASA was out of business. We're not out of business. And so in December of 1998, we took up the first US segment on the bottom, the US node, and grappled the first Russian segment, and we were the first crew to go inside, turn on the lights. From a professional standpoint, that was a real highlight to make that call. Houston, this is the International Space Station. So what's that look like today? You know, it's as big as a football field, can support a crew of 6. We've transitioned to doing probably about 40, 50 hours of scientific research per week. So very active. It is considered a U.S. national lab, a U.S. national lab designation. Beyond that, we are developing our next generation spacecraft, a multi-purpose crew vehicle, also called the Orion. Just last December, it flew a test flight. Of course, this is for missions beyond low Earth orbit, and it also very characteristic design. In fact, some of the Apollo astronauts who are still around call it Apollo on steroids. So it's sort of like Apollo, but much bigger vehicle. Initially was designed to carry 6, but it was so big we couldn't get it off the ground. So now it carries 4 and parachutes back to the water, as opposed to landing like a glider, like the Space Shuttle did. So this is a test flight that occurred in December. The whole flight took about 4 hours. Very, very successful flight to check out all the systems. Launched on a Delta IV Heavy out of Cape Canaveral. Lots of good days coming back from this flight. No people on board, but a heck of a lot of instrumentation on board. And we'll have a couple more series of flights, test flights, before we do put humans on it in the next few years. The other thing that we're doing that you probably heard about is there's a commercial crew program. And so we've come a long way since our post-accident days, because folks are challenging NASA to get out of low Earth orbit. Sort of the been there, done that. You know, you guys have done that. Let's turn that over to the commercial sector, especially the ferrying of astronauts to and from the International Space Station. As you might know, right now we have to rely solely on the Russians, on their Soyuz vehicle. They have experienced some problems. They just experienced another problem a couple weeks ago with the Progress vehicle. We're looking at some of the similarities between those two systems to determine whether or not the next launch is safe. But we have very, very limited insight into the Russian system. And so we have contracted with 2 companies. Boeing has the CST-100, they're both capsule designs, and SpaceX, it's a human version of their Dragon spacecraft that's already flying as an unmanned spacecraft, carrying supplies back and forth to the International Space Station. So what's our role in it? We're going to take on a new role. NASA's role in this vehicle will be to look at the certification of those vehicles and to make sure that it meets all the requirements and safety mandates for human spacecraft. As I said, the Columbia Accident Investigation Board told NASA, not really asked, told NASA, pretty direct words, establish an independent technical authority. And you can see at the end of that statement, what they really meant is it should have no connection or responsibility for schedule or cost back to the program. So that engineer shouldn't be matrixed to and working for a program manager, because if he tells that program manager no too many times, he might be thinking, well, I'm not going to get my performance award this year, or I'm not going to get my promotion. The program manager should also not be able to say, I can't tell what you safety guys are providing me with, so I'm going to cut you by 50% next year because I've got some budget issues. Or you systems engineering and integration folks. As I said, they were highly critical of the safety organization. It's a famous comment, there's no there there. So the genesis of that comment was they would say, well, where were the safety guys during all these discussions? Oh, they were there. They were in the room and they were breathing, but they weren't talking and they weren't bringing anything to the table like a risk assessment or probabilistic risk assessment or talking about the hazard controls. They were there, and that was about it. Hence, the organization I'm with now was established. So if you remember that the Columbia accident took place in February of 2003, it was just a few months later that my organization was established. The first leader of that organization, who stayed there for 10 years, was the Shuttle program orbiter project manager at the time of the accident. Now, the accident wasn't his fault. As I said, the orbiter was not designed to fly through a debris field, but he was fired. But they decided who better to put in charge of this organization than somebody who has lived losing a vehicle and a crew. And, you know, we're close to these people. This guy had been a launch director as well down at the Cape, knew him well. There is nobody more passionate about safety than Ralph Rowe is, who is now no longer in charge of the NASA Engineering Safety Center. He is the agency chief engineer. So our safety philosophy was based on 3 tenets: strong inline checks and balances. Checks and balances because people can make mistakes, but we're in such an unforgiving environment, we need to catch and correct those mistakes. The next one down, and I don't know if those of you who are in business know what I mean by healthy tension. So trust me, when you tell a program manager, no, you can't do that, and this is what I have to do, or I need a series of 10 more tests, or I need to go, you know, to an acoustic chamber and do some testing, and it's going to cost you $1 million. He's not too happy with you. So we call that healthy tension. And then the last bullet is value-added independent assessment. We really think there's a lot of value in bringing in an independent but highly educated, highly astute team to look at some of these critical programs. And again, one of our tenets is fostering that open environment, an environment in which everyone can speak up. So the way in which we operate is based on a tiger team approach. So let's say, for example, the International Space Station, I'll knock on some real wood if there's any around here, experiences a problem later today. We will immediately form a tiger team, a team of individuals that just come in and start working that problem. You know, think of it as in, you know, the movie Apollo 13. You know, there's a bunch of guys, a bunch of tools and equipment. What do we do now? And we've gotten pretty good at that over the decades. We also have technical fellows. And so we have technical fellows within the agency that have established technical discipline teams. And we've created this ready network of experts from NASA, from other government agencies, industry, academia. And we have that diverse and expertise to bring to bear on almost every problem. And again, at the bottom, we have a very strong systems engineering and integration function because we have found that time and time again, it's at the interfaces of these complex systems where the majority of the problems occur. So our organization is very diverse. We have about 60 employees that are spread out all over the country. And so we have 10 NASA centers, you know, from Houston to NASA Glenn in Ohio, to the Cape, to JPL out in California. And so we operate everything remotely via video telecoms, almost all of our meetings, and it's always I always feel sorry for the guys on the West Coast because we consistently call 8:30 in the morning meetings, and then eventually they get us back and they say, let's schedule a 5 p.m. meeting, so the East Coasters get to have some fun with that. But as I said, we have 17 technical fellows. They range expertise from aerosciences, mechanical systems, environmental control system, loads and dynamics. And then we have 2 other technical discipline teams that are more focused on operations, one for human spaceflight and one for robotic spaceflight. So you can see we draw on over 700 people nationwide. Now these aren't full-timers, so I'll need expertise in polymer chemistry. I'll get some recommendations either from industry, academia, get in touch with them, say here's how many hours, here's about how many months I need you to help us, can you come on board to help us? We've done this for well over 10 years now, and most people tend to, unless they absolutely cannot, drop what they're doing to come help us because they know it's some pretty interesting and very high-level problems that we work on. So again, our technical fellows are very senior level engineers and scientists. They are the agency's leading experts, and then they form these technical discipline teams and have a network of expertise throughout the nation. And I say nation because many of the topics that we deal with are international trade sensitive and have to be restricted to U.S. only residents. There's just a quick slide showing the assessment teams. So we have our core teams, you can see all the disciplines represented, and then as I said, we bring in, including other NASA engineers. When we first proposed this very highly matrix organization where only really a few people work for the organization. So we have 17 technical fellows, we have 4 principal engineers, of which I'm one of them, and we have 10 chief engineers. And the rest of the engineering expertise from NASA comes from the line organizations. And the manager said, you're not going to take my people. It's not like they're sitting around doing nothing. When you have a problem and you say, hey, I need them to work on this NESC project, that's just not going to happen. Well, 10, 11 years later, that's exactly what happens, and they're thankful for it. They're thankful for that breadth of experience, especially for the younger engineers, and know that we're working on the agency's top technical risks. So it just goes to show, you might have some very innovative, creative thought in terms of what a very highly matrix organizational structure can look like. You might get some pushback, but you have to try it a couple times and see what's workable, and this is proven to be a very workable situation. So here's just some examples of what we've worked on over the years. Everything from radio phase sheet damage on the International Space Station. We're scanning the camera systems and we notice some damage. We also have an issue with the solar array mass buckling as we go into shadowing events, and we get differential temperatures across that large mass. To a particular that I'm working on, we've had some issues with the Orion heat shield recently. We had 2 different issues with the heat shield that launched on that flight that I showed you the video from December. And we had cracks. These things are done in gores, and between the gores there were a lot of cracks showing up. Turned out Apollo had a very similar system. We call it a monolithic system. It's a honeycomb and it's impregnated with the ablator. You can see how the ablator is put in. It's put in by hand, very process sensitive. Would love to transition to a robotic procedure, but instead we're actually changing the architecture, entire architecture of the heat shield, and going to a block system. So that's my next assessment. So for this, as I said, we needed experts in polymer chemistry. We traced it back. You can see the low material strength that we were experiencing as compared to when we did some test panels and computed our engineering allowables. We traced it back over a extensive, in terms of, I think we've done 4,500 tests. We traced it back to an issue with the primer that's used before you put the ablator in. And so then we needed some expertise in priming. So we found a company that has expertise in priming everything from pharmaceuticals to oil and gas. And the issue we're having there is You're doing an external spray of the primer. You're doing it into a 2-inch honeycomb structure, getting buildup at the OML, not too much primer at the IML. That buildup of primer at the outer mold line, as you go through the temperature to heat it and the temperature to cure it, causes bubbling in the primer. And those bubbles effectively serve as stress risers and create these interface strength issues. And so that's our little strength issue. Who would have thought? We trace it back to the primer. So luckily, if we told the program manager, hey, do you mind if we go spend about $2.5 million and do 4,500 tests and have a team of 50 people working on this, he probably would have said, I can't afford it. So we don't have to ask. We have our own separately funded organization, and we have our reach back capability to all the expertise that we need. One of the other things we're working on is take very seriously spacecraft occupant protection. As I said, we were able to recover the crew and do analysis post-accident and determine injury patterns, and we are trying to make the vehicle as safe as we possibly can. And so we are using, for the first time, believe it or not, NASA didn't do too much of this testing in the past. We're using anthropomorphic test dummies ranging from 5th percentile female to 95th percentile male, and doing a horizontal impact sled test as well as vertical, and then comparing those to analytical models. And then for the commercial activities, one of the best things we can do is that top bullet is to share our best practices and lessons learned with our new commercial partners. Even though they have expertise in flying unmanned systems, it's a totally different spectrum as soon as you start putting humans on board that space flight. So we're trying to educate them in terms of the level of rigor, level of redundancy in the systems that is required to have that reliability to fly people on board. And I talk about reliability, it's nowhere near the reliability, let's say, of a commercial aircraft. The typical goals that we look for is a loss rate of 1 in 200. About a 1 in 200 risk. We recomputed the risk of what it really was after we learned everything we could about what took down Columbia. When Columbia flew, we thought the risk was about 1 in 200. What it really was 1 in 56. We were accused by our managers, even though that probabilistic risk assessment took 2 years, we were accused of our managers of taking 113 flights and dividing by 2, which is the number of accidents we had, and coming up with that number. I wasn't real pleased with that. That was one of my more classic meetings. Because we literally had spent over 2 to 3 years perfecting the models, and it came out to be 1 in 56. Well, that's what the risk really was. Interestingly enough, the next question was, how do we go tell Congress that we just stood down for 2.5 years and our risk is 1 in 56? So it's communicating the risk, and we had to communicate. We thought that risk was 1 in 200. It wasn't. We were kidding ourselves. This is what the risk was. This is all the mitigations we put in. And if the risk is ever below 1 in 200, it requires the administrator of the agency, who's appointed by the president, to say go for launch. And he's had to do that more than once. So in summary, we've been in place for 10 years. And in that 10 years period of time, we have been called in on 500 technical assessments. Occasionally, we're called in by outside organizations. We were called in for the F-22 oxygen generation problem. We were called in for the Chilean miner rescue. We were called in for the Toyota unintended acceleration issue. Those are fairly rare. I don't ever get to do that because I'm our human spaceflight expert, and they keep me very busy in that realm. Some of those are much more geared to our daily programs and projects. So at the bottom, I see, that strong focus on safety and mission assurance is really easy to do in that post-accident time frame. And it's much harder to keep that same level of vigilance that's required in the following years. But I was sitting in a meeting, as I said, we're coming up on this time frame where vehicles are getting much more mature. Our commercial partners are a couple years away from flying. We're in the midst of flying unmanned test flights on our Orion, and then we'll eventually fly people. within the next 5 years or so. As we get closer and closer to flight, more dissenting opinions are coming up. And we were talking to the engineering manager at Johnson Space Center the other day about some concerns we had. We call them weak signals that we see in the community. Are people really speaking up? How are we running meetings? How are we communicating with the programs? And so we made a little presentation to our engineering, our safety, and our program folks just last week. And one of the things the engineering manager, who's a friend of mine, said is, you know, everybody in this room, we live Columbia, you know, and that is never going to leave us. And it's times like this where we have to remember what we felt right after Columbia and how we vowed that would never, ever happen again under our watch. Ironically, I left that meeting, I came back to my office, and there was a meeting on my schedule, and I didn't know what it was about. And in walks an engineer who's worked at NASA about 2 years, and the director of human resources. And she says, I wanted to bring this young engineer to talk to you because he's got some concerns. And he started by pulling out the Columbia Accident Investigation Report, and he said, I've been reading this. I've been reading this every day, and I've been reading what happened. You know, he was probably in grade school when Columbia happened, you know, maybe junior high. And I've been reading, I wasn't here. But you know what? Some of the things I see today are exactly what I'm reading in this report. And I'm worried. I'm worried that all these folks who are in the agency now that didn't live this accident don't have those lessons learned. What can you do to help me communicate that? And so we're going to start a series of brown bags and talking again about the Columbia accident. It's been 10 years. 10 plus years, to remind them of those failures that occurred and what we should be vigilant of in our culture, in our organization, and in our engineering practices. Last thing this crew ever wanted to do, or my friends, is for us to stop flying. They want us to continue. They want us to continue safely, though. The one thing that you know, my then 16-year-old daughter said was pretty prophetic. I had to wake her up and tell her that we'd lost Columbia, and I had just flown the year prior on Columbia. So I woke her up and told her, and she went through 4 flights with me. In fact, my first flight, I was a single parent, and kind of did it alone. And she said, you know, I stood on that runway 4 times, and never once did it occur to me that you weren't coming home. And so every time I sat in a flight review, it's my job to give the crew's family that same level of confidence that their family members are going to come home safe because we've done all that we can. And it's not safety at all costs. It's never going to be no risk. This is exploration of space, and it's risky, and it's one of the highest risk professions in the world. The loss rate is pretty phenomenal when you look at the numbers, and it's well worth the risk. But even in that very risky environment, we should do everything we can to help to ensure the safety of the crew. So I hope that in this talk today that even maybe if you don't work in an extremely high-risk environment, there's something that you can take away, that you can take back to your organizations to do that introspective look, to take a look at your culture, the safety in your organization, and maybe the engineering practices, and maybe make a better organization out of it. So thank you very much.